In 1878, the Midland Railway completed a brick viaduct across the Welland Valley between Northamptonshire and Rutland. It carries a single railway line. The valley it crosses is wide and flat and unremarkable. The viaduct is not. 82 arches, 30 million bricks, 1,275 yards from one bank to the other, just under 3/4 of a mile. The longest masonry viaduct across a valley in the United Kingdom. It was built in 4 years by a workforce that peaked at 3,000 men, working in ground so difficult that the construction company appointed a surgeon specifically for this contract. The line it carries has been freight only for decades. The viaduct has not been replaced. It has not required replacement. 30 million bricks laid into the Welland Valley clay in 1875 are still carrying load in 2024, 146 years after the last brick was laid. By making a small gesture and clicking the subscribe button beneath this video, you perform a small action with great significance to us. By pressing it, you understand that the matter is not about the magnitude of the act, but its meaning. It shows that the effort, the late nights, and the discipline required to bring this forward mattered to someone on the other side of the screen. Like the video, subscribe to the channel, even leave a comment below suggesting which structure you would like us to cover next. The Midland Railway, in the 1870s, faced a routing problem. Its main line between London St Pancras and Nottingham passed through Leicester, and the Leicester section was becoming a bottleneck as traffic volumes grew. The solution was a new cut-off route, 15 miles of fresh line from Kettering, northward to Manton Junction, bypassing Leicester entirely. 15 miles of new railway sounds straightforward. 12 of those 15 miles were through relatively gentle Northamptonshire farmland. The remaining 3 miles crossed the Welland Valley, and the Welland Valley required something that could not be built cheaply. The valley at the crossing point near Haringworth is broad and flat, carved by glacial action through the local ironstone and limestone geology. The River Welland runs along its floor, slow and wide. The valley bottom is clay, alluvial deposits laid down over thousands of years, soft and compressible, offering poor bearing capacity for heavy foundations. The valley sides slope gently upward to the plateau farmland on both sides. The height difference between the valley floor and the required rail level was approximately 60 feet. To cross this on a gradient that would allow loaded freight trains to operate without excessive effort, the viaduct had to maintain that height for a considerable distance on either side of the river itself. The structure that resulted was not determined by the width of the river. It was determined by the width of the valley. The contract was awarded to Lucas and Aird, one of the largest civil engineering contractors then operating in Britain. John Aird had built the 7 tunnel approaches and numerous major railway works across England. He understood difficult ground. At Haringworth, the ground was worse than preliminary surveys had fully indicated. The clay valley bottom that had to support the pier foundations was not uniformly soft. It varied unpredictably in bearing capacity from one pier position to the next. In places, the foundation excavations had to go considerably deeper than the drawings specified, reaching down through the soft alluvial clay to firmer material before the concrete base could be poured. In others, the clay was stiff enough to allow the designed foundation depth to stand. Each of the 82 piers required its own assessment of the ground beneath it. Each foundation was built to what that specific location required. This was not a standardized foundation type applied uniformly across the site. It was 82 individual engineering decisions made in the ground, one at a time, across a site 1,000 yards long. Construction began in 1875, with a workforce that grew rapidly as the full scale of the task became apparent. At peak, approximately 3,000 men were employed, quarrymen cutting and transporting the Peterborough red brick from the local clay workings, labourers excavating pier foundations by handshaft and pick, bricklayers laying course after course of the dense engineering brick that forms the body of the structure, and the carpenters and iron workers, maintaining the timber centering that supported each arch ring during construction until the mortar had cured sufficiently to carry the load. The work was dangerous beyond the ordinary hazards of Victorian civil engineering. Excavations in soft clay at depth could collapse without the warning that rock excavations generally gave. The construction company's appointment of F.W. Brown as resident surgeon specifically for this contract was a practical acknowledgement of the injury rate that work of this kind on this ground would produce. The records document individual deaths from shaft collapses, from falls from the arch centering, from accidents with the heavy materials moving continuously across the site. The viaduct was built at a human cost that the structure itself carries no record of. The brickwork is Peterborough red, a dense, hard-fired engineering brick, sourced from the clay beds around Peterborough, a material chosen specifically for its low water absorption and high compressive strength under sustained cyclic loading. Each of the 82 arches spans 40 feet. Each pier rises from its concrete foundation to the springing line of the arch above, in a tapering form, wider at the base than at the crown, transferring the load from the arch ring down through the full height of the pier into the ground below. The mortar throughout is hydraulic lime, not Portland cement. Portland cement in the formulations available in 1875 could produce brickwork that tested stronger in the short term, but was more brittle under the repeated flexing that a loaded freight line imposes on its structures. Hydraulic lime cured more slowly. It was less dramatic in its early strength gain. Over decades and over centuries, it produced brickwork that moved slightly with temperature and load cycles rather than cracking under them. Lucas and Aird specified hydraulic lime because they had built enough Victorian railway infrastructure to understand what failed first. Their specification at Haringworth reflected that knowledge. The mortar is still in the joints, 146 years later. The viaduct was completed in 1878, and the line opened for traffic. The structure performed exactly as designed. Loaded freight trains crossed the 82 arches at the permitted speed. The centering was struck arch by arch as the mortar reached its working strength, and the brickwork carried the load without incident. There was no drama at the opening, no last-minute concern about a critical pier, no emergency repair before the first inspection. The Haringworth Viaduct was built by an experienced contractor to a deliberate specification, and it worked. The absence of drama at completion is, in retrospect, the whole point. A structure built to sufficient excess does not fail at its opening. It does not require urgent modification in its first decade. It simply performs, continuously and without incident, until the purpose it was built for either ends or evolves into something its builders could not have anticipated. The Kettering to Manton line carried regular passenger services until 1966, when the route was withdrawn under the beaching rationalisation of the British railway network. The passenger trains stopped. The viaduct did not stop carrying trains. Freight traffic continued, and continues today, aggregates, steel, and general freight, moving on a route that has outlasted the passenger service it was originally built to support. When the passenger trains went, a less well-built viaduct might have been closed alongside them. The line to a structure of less certain condition would not have been worth maintaining for freight volumes that were, for many years, modest. The Haringworth Viaduct was in good enough condition that closure was never seriously considered. The cost of keeping a sound structure operational was lower than the cost of replacing it, or of building a road equivalent to handle what freight it still moved. Soundness, it turned out, had an economic argument as well as an engineering one. Network Rail's structural engineers have assessed the viaduct repeatedly over the decades since it passed from British Railways into the modern infrastructure management regime. Some sections of mortar have been repointed, where rainfall erosion has worn the joint face below the intervention threshold. The brickwork itself, the Peterborough red engineering brick laid in the Welland Valley between 1875 and 1878, shows no structural deterioration requiring intervention. 146 years of loaded freight trains, of Welland Valley frost cycles, of the lateral wind pressure that crosses the open valley, unimpeded for miles in both directions, have not shifted the piers. The concrete foundations poured into ground that varied unpredictably from one pier to the next have not settled unevenly. The 82 arches carry load today within the structural margins the original specification allowed. Stand at the valley floor near Haringworth on a clear morning, and the viaduct fills the view from one side of the valley to the other. 82 arches in a gentle curve following the natural alignment of the valley, the piers stepping down to the valley floor and rising again on the far side. The brick is weathered to a deep, settled red. The mortar joints are tight and even. The structure does not look new. It does not look distressed. It looks like something that has been there long enough to belong entirely to the landscape it crosses, which is precisely what it is. A freight train crosses perhaps twice in a working day now, where the line once saw a continuous service. The viaduct carries each one with exactly the same geometry and exactly the same structural response that it delivered to the first train, 30 million bricks to cross one valley. The Midland Railway spent that because the alternative, a lighter structure, a narrower specification, something optimized for the minimum required load rather than for the maximum likely load over an indeterminate service life, would have required intervention or replacement within a timescale that the traffic revenue could not have justified. The engineers of 1875 did not frame it in those terms. They framed it in the terms available to them. What does this ground require? What does this traffic require? And what material and form will serve both requirements reliably for as long as the line is needed? The answer was 30 million Peterborough red bricks laid in hydraulic lime mortar across 82 40-foot arches in the Welland Valley. The line is still needed. The viaduct is still there. Here again you see a mega structure born from the intelligence of a talented engineer. If you would like more videos like this, please like the video and subscribe to the channel.